So this is Math466 Advanced Applied Analysis, Lecture 15. Because I'm teaching at the elementary school today and I want to be able to say that this was done in a college class, we will start the day with the game. This is actually related to something you've all seen from a previous class you've taken with me. And since there's only one class I think you have all taken with me, you should be able to figure out what class that is, and then maybe you can figure out what the quantity is or what the perspective is for this problem. So it's called the Hershey bar game. If it's tough to understand this as an abstract math formulation and you want me to buy Hershey bars and bring them to class, I am happy to do that. I cannot do that at the elementary school because that would be bringing in food. But if it would help to have an actual Hershey bar to play with, I'm happy to do that for a future class. So the way the game works is as follows. You have an m by n grid. And then on each turn, you make either a horizontal or a vertical cut. And then whoever makes the last cut wins. Obviously, it's two players and alternate. Just making sure it's recording. Yes. Two players. So for instance, the first player might choose to cut right down the middle. And so maybe we go to the following. And then maybe the next player chooses to cut this block over here. And so on your turn, you choose a piece to cut and do either a horizontal or a vertical. So in all of these games, the question is, does someone have a winning strategy? And if so, what is it? So you've all figured out that the class you've seen this in is operations research. And I believe we did an example of a game where it's known that somebody has a winning strategy, but we don't know what it is. This is a game where you can actually compute who has the winning strategy as a function of m and n. So let's say it's m and n over here. And you can even figure out what that winning strategy is. So it's nice when you can make things explicit. It's sometimes not so useful to be able to tell somebody, there is a solution to your problem, don't worry. What's the solution? Well, I mean, that we don't know. And I know some of you are planning on being consultants. It's nice to at least be able to tell them the problem can be solved, but that's not going to be enough to keep your job. You have to either tell them how to do the job or how to get close. So any thoughts on who has the winning strategy as a function of n and m? Last cut wins. So what should you do in something like this when you're trying to get a sense of what's going on? Smaller grid. So start with a small grid. Build intuition. So what's the simplest game we could play?
One by one.
The one by one. So the question is this even a game?
Yes. Player one loses.
So it's whoever makes the last cut wins. So this is where, unfortunately in this case, it's not clear what's going on with the one by one as to is there even a cut. I'm thinking right now to the Jets fumble with the pylon as to, anyway. So the one by one I think is too small to build intuition. So the first one we can really do is the one by two. So we can make a little table here, m and the outcome. So who has the winning strategy in this case? Player one. Okay, and what's player one's strategy? Cut. Oh, thank you, m is 2. Right. And similarly, if we did 1 and 2, so we might as well assume maybe m is greater than or equal to n by symmetry. So there's really only one move. Take it. OK. What should we look at next? Two by two. Things are actually small enough that it's fairly nice. How many moves does player one have? One. By symmetry, the vertical and the horizontal cut are the same. So player one has to cut to this. How many moves does player two have by symmetry? One. Has to cut the top. So this was player one, player two, and now player one has the only possible move. And so what do we get? Player one wins. So I'm seeing a pattern. What do you think the pattern is? Ah, OK, so you're being very careful. So a lot of people, when they say, well, player one maybe always wins. So when you start to have a pattern, what you want to do is you want to choose something that could potentially disprove it. So I'm in the middle of reading The Black Swan. How many of you have read this? Terrific book. And so it talks about how dangerous it is to make predictions based on the past. If you're in what he calls mediocre, you might call it like mediocrestan, or where things that for the most part you don't have very large deviations from the average values. So if you look at the height of people, you're not going to find somebody who's 70 feet. And then you have extremistan, where you can have some extreme events that are very unlikely, but can happen and are just far beyond what you would normally get. So you could look at website hits. One of the best examples he gives about the danger of making incorrect inferences is, imagine you are a turkey. After a while, you realize that the purpose of humans seems to be to provide you food. And every day the humans provide you more food. These are lovely people. And with every passing day, you become more and more convinced that you have correctly understood what humans do, until the day before Thanksgiving, where they put you on the chopping block. And so all of a sudden, that real event happens. So when you have a sequence, you want to choose something that would be very different. So here, what was noticed is that maybe everything here is even in terms of their product. So let's try something that's odd. So it would be a good odd choice. 3 by 3? 3 by 1. Right? Let's make things simple. And so if we choose a 3 by 1, it's really nice with these small values that, how many choices are there? How many opening moves do we have? But 1 by symmetry. So player 1 has to go like this. And now how many moves does player 2 have? 1 by symmetry. And now player 2 wins. So it's beginning to look like maybe if the product of M and N is even, there's a winning strategy for player 1. If the product of M and N is odd, there's a winning strategy for player 2. It's a little bit difficult now because we've only looked at small things. We could now look at a 4 by 4 grid or a 3 by 3 grid, where you now have real moves and real choices. So let's imagine in the interest of time we've done that. Anybody want to give me a guess as to how you would prove if the product is even, you win? If the product is odd, the first person loses.
I think there's some proof that it takes n times n minus 1 cuts.
Yes. So that's an outstanding conjecture. No matter how you cut, you need m times n minus 1 cuts. If m times n minus 1 is odd, player 1 wins. If m times n minus 1 is even, oh no, I did, yes. Player 2 wins. Or equivalently, player 1 wins if m times n is even, player 2 wins if m times n is odd. How many of you have ever watched the movie War Games? All right, I'll try to remember to do a clip. This is an old 80s movie with Matthew Broderick. There is a defense computer that takes control of the US nuclear arsenal, and they're trying to convince the computer not to start World War III, and trying to teach the computer, don't play nuclear war. You have seen this, yes. And I won't give things away. It's an interesting movie. What do you think player 1's strategy is? Let's say it's odd. If odd, what's the strategy? Play the game. So it'll be interesting to see, if the 5th graders are able to detect this. All you have to do is play, no matter how you play. You might remember the triangle game we did in operations research, where I offered, I think, 20 Canadian if anybody could prevent me from getting a 0, 1, 2 triangle. And I said, I'm even willing not to make any moves. I'll let you fill in everything yourself. As soon as you agree to play the game, I win. So why does this work? Did we do the infection problem in operations research, where you have a grid and you infect cells, and if 2 of your neighbors are infected, you're infected? And we saw that there was a monovariant we could associate it to the infection. The perimeter of the infection never grew larger. It could get smaller, but it could never grow larger. And so if we only infected n minus 1 cells on the n by n grid, the maximum perimeter is 4n minus 4. It can't be the entire space. So there must be at least 1 cell that's not infected. We want to associate a monovariant to this. A monovariant is a quantity that can only move in one direction. It either stays the same, or always goes down, or always goes up. What do you think would be a good monovariant for this game? On each turn, we want to associate something to the game state. So if we come over here, I want to create a monovariant, and I want to give it a value here, and a value here. Any thought as to what my monovariant should be?
Number of cuts left.
You could do number of cuts left, but then you have to prove that you can actually determine what the number of cuts left are. There's something that's equivalent to that, but much easier to prove. So when you look at this, what would you want to associate to each?
The number of groupings?
Yeah, the number of pieces. How many pieces do you have in the first one? In the second? In the third? So the monovariant is number of pieces. Number of pieces. Every time you cut, what do? You increase the number of pieces by 1. You start with 1 piece. How many pieces must you end with? So each cut adds exactly 1 piece. Start with 1 piece, end with mn pieces. So we need mn minus 1 cuts. And what's nice is because every time you cut, you get another piece. You get exactly 1 piece. And we know at the end of the day, imagine you had a piece that was 1 by 2. Well, then you could cut it and you're not done. So you know you have to keep playing until you're down to just all 1 by 1 pieces. So I will probably be doing things like, oh, geez, I wonder where I should go right now. Yeah. So this is where you do some showmanship with the little kids in terms of how you decide which move to do. Where you go, oh crap, you moved there? So now how do you think I might stack the game? A lot of nice alternatives or options if you know mathematics, right? So if I'm going second, what kind of board do I want?
That one.
Why that one? It's 25. And I'll win on an odd board. And so, what I like about this is you have this beautiful idea of a monovariant. The other thing is, and we don't do this nearly enough, start with a simple case and build up some intuition. And so if I give you, a 5x5 board to start with, and I told you, draw a big board, I don't want you to have something small where you can get a sense of what's going on. I want to try to put blinders on you and have you look at the wrong thing. The other thing which would be good to look at is to look at maybe a 1x5 board, a 1x6, or 1x7. Look at it in generally like a 1x(n) board. And try to understand what's going on in that case, because that case is simple. So understand simple cases as well as you can, and then build up from that. Okay. So it's time to turn back to Benford and stuff. So we've proven Kroneker's theorem that if alpha is irrational and alpha mod 1 is equidistributed. We saw that this allowed us to use resultant Fayet's theorem. We did not need to use Dirichlet's theorem, which is great because Dirichlet requires differentiability. The big idea was we approximated the characteristic function of an interval with a nice continuous function that was close, and then we approximated the continuous function that was close with trigonometric polynomials. And the trigonometric polynomials were nice when we evaluated them at xn, which was n alpha mod 1, because we can drop the mod 1, and then we have geometric series. We understand geometric series. Okay? This is basically the only series we really understand. We can give something like the exponential function a name, and it does have some nice properties, but the geometric series, that's our go-to result. It turns out more is true. You could study n to the k alpha mod 1. And that is also equidistributed. But it's a little bit more work. Also equidistributed if alpha is irrational. Similar ideas, more algebra. I'm not even going to ask if anybody wants to see the general case with more algebra on the board. By this point, you are all seniors, and you know enough not to want to see this in public. It's in the book. If you want to see it, by all means read it. If you want to talk to me about it, I'm happy to talk to you about it. It's essentially the same ideas. You need a little bit of new thought as to how do you handle the n to the k. That's the interesting part. But the general framework is very similar. I want a good function. I want to approximate. I want to reduce it to a trigonometric function. And I want to study like the sum, and it goes from 1 to n of e to the 2 pi I n k alpha. And I reduce this to studying something like this. And the problem now is because now I have a k here, it's no longer a geometric series. So a little bit more work is needed. That's where the new ingredient comes into play. Okay. So what I want to do now is I want to show how this implies certain types of recurrence relations of Benford, and then go from that to discussions with you as to what is our next thing to study. Out of curiosity, how many of you went to the colloquium where they proved the Heisenberg uncertainty principle? Okay, so since no one seems to have gone to that, we will do that at some point. This is one of the nice applications of Fourier analysis. Basically, Heisenberg uncertainty principle says you cannot simultaneously measure with infinite precision a particle's position and momentum. That your uncertainty in the two, if you take that product, it's at least a certain amount. In the right system, I think it's h bar, which is, I think, Planck's constant over 2 pi. It might just be h. Well, h bar is h over 2 pi.
Yeah.
I think it might just be h bar. But if I'm off, I'll just change my units a little bit. But there's a fundamental precision you can have. Now, for most things, it doesn't really matter. If you're measuring the moon, you shoot a photon of light, bounces off the moon and comes back, and you know where the moon is, but now you've given the moon a little bit of a boost. Well, the amount of a boost a photon gives to an object like the moon is insignificant. We don't have to worry about that. But on the subatomic scale, if you want to know where an electron is, when a photon slams into it, it gives it an enormous boost. It turns out the Heisenberg uncertainty principle is really just a statement about a function and its Fourier transform. So I will just state this as for future. So if I have some function f, such as say absolute value of f squared equals 1, I'll have f hat. And what I will do is we will study basically the variance of f, variance of f hat. And it turns out that you cannot simultaneously, I'll probably want to do maybe absolute value of f squared and maybe something like that. It turns out that this cannot be too small, that this is greater than or equal to some universal constant. And what do you think that constant will involve? Which constant do you think will play a role? Well, no, now we're doing this as a math statement. Planck's constant can't come into a math statement. Pi. There's got to be a pi somewhere involved. The Fourier transform is built with pi's. So our constant is going to have a pi coming in. And this is where I think the 2 pi comes in Planck's constant. Because Planck's constant was defined in some other place. It's amazing that it emerges here too. The physics is that f somehow, or its magnitude squared, represents the position distribution of the particle, and f hat squared represents the momentum distribution of the particle. That's where the physics is. That these quantities can be modeled by a function and its Fourier transform. But then it's a math statement that I can't simultaneously localize both the function and its Fourier transform. If you think back to the Dirac delta functional, this was the function that was essentially plus infinity at the origin and 0 everywhere else. So that's our delta spike. Let's calculate the Fourier transform of the delta spike. So it'll be the integral from minus infinity to infinity of delta of x e to the negative 2 pi I xy dx. What does this equal? So I'm integrating the function e to the negative 2 pi I xy against the delta spike. What do I get? I'm sorry? At what point? For what value of x? 0. Yeah. So I just get back the value of this exponential at x equals 0. So the Fourier transform is identically 1. You want to talk about having no information. This is completely spread out over the entire real line. All places look the same. This is complete information. And then you can ask which function maybe temporizes best between the two extremes. Where, I can get better and better accuracy on the position at a cost of having less accuracy on the momentum. Any thoughts as to what function might be a really nice balance between the two?
E to the minus x squared.
Yeah, which is what kind of function is e to the minus x squared? Up to constants. E to the minus x squared, what it has a name. It has at least 3 names. Normal distribution, bell curve, Gaussian. The Gaussian will be great in terms of trying to equalize both of these. So this is something that I want to do because if you haven't seen this before, it's a nice application of Fourier analysis. And it's a nice way to talk about the difference between math and physics. At the end of the day, if you're doing something like physics, the math has to be applicable. And a lot of people try to say, well, the solution to this differential equation must exist because this models the planets. And the planets have some kind of stability orbits. So there must be a solution. No. There's only a solution if you actually can prove that your mathematical model correctly models the physical world. We hope it does. We think it does a good approximation. So we're trying to develop mathematical tools that you can apply elsewhere. But a lot of times the difficulty is figuring out how to interpret things. How do we interpret these quantities in a physical setting? Well, the idea is that in physics, you can somehow convert these to position and momentum operators. So this will allow us to talk about some nice applications of Fourier analysis. I want to go back to Benford and do recurrence relations. So we'll do the Fibonacci's for now. So we know Fn is 1 over root 5, 1 plus root 5 over 2 to the n, minus 1 over root 5, 1 minus root 5 over 2 to the n. And we can write this as Fn is 1 over root 5. I'm going to use the golden mean for this. So golden mean to the n, 1 minus, and it'll be 1 minus root 5 over 2 over 1 plus root 5 over 2. So it'll be 1 minus root 5 over 1 plus root 5 to the n. Okay? What's 1 minus root 5 over 1 plus root 5? How do we make this into a number that's a little bit easier to look at?
1 plus root 5 over 1 plus root 5 from 1 minus root 5.
I'm sorry?
You subtract 1, add 1. Or sorry.
Not subtract 1. So how do I make sense of a fraction like this?
Multiply
Yeah, multiply by
1 minus root 5
by 1 minus root 5 over 1 minus root 5. Then the denominator becomes 1 minus 4. So we get Fn is 1 over root 5, golden mean to the n, 1 minus. Now we'll have 1 minus root 5. So we have a negative 4 down below. And what does the top become? 1 minus root 5 times 1 minus root 5. So we'll get 1 minus 2 root 5. And then we'll have a plus 5. So we get 6 minus 2 root 5 over negative 4. Okay? Or if we want, this is 1 over root 5, golden mean to the n, 1 minus 2 root 5 minus 6 over 4. So there's a lot of different ways of looking at this. Is this really close to 1? How large is the top? Root 5 is about 2 point something. So what's 25 squared? 25 squared is 625, right? So 2.5 squared is 6.25. So this would be a little bit less than 2.5. You want to be able to get a quick ballpark estimate. So this numerator, is on the order of a quarter, a little bit less than a quarter, right? So when I divide by 4, this should be about like 1/16. The golden mean is only about the size of 1.6. So this is significantly small. Even when I multiply by the feet to the n, it's small. But we know it's small when we multiply by feet to the n because it's just this thing over here. So if I wanted to look at logs of this, the log of Fn would be the log of 1 over root 5, which is a constant, and log phi, another constant. I'm sorry, and log phi, which is just nice. And then we would have the log of 1 minus this. So the reason we want to write it like this is when we did all of our stuff on recurrence relations, we got this nice closed form expression. But when we wanted to use Kroneker's theorem, we didn't want to have an error term. We wanted to have something that was exact. I don't want to take the log of a difference. The log of a difference is very hard to work with analytically. But the log of a product is the sum of the logs. So really, the main point of today's lecture is just how do you want to attack small errors. We want to study the log of the sequence mod 1. And because we want to study the log of the sequence mod 1, I don't want to write the Fibonacci numbers as a difference. I want to write the Fibonacci numbers as a product. The first piece is going to be constant, so it's not going to matter when we take the log. The second piece, the phi to the n, that's going to become the n log phi. That's what we know is equidistributed. That's great. And then the last part is going to be the small error. So what we get is we get the log of fn is the log of 1 over root 5 plus n log phi plus the log of 1 minus 2 root 5 minus 6 over 4 to the n. And by writing it like this, we have the log of something that's really close to 1. So because this is really close to 1, can this have much of an impact? No. Now, we know that n log phi is equidistributed. So if you have a sequence that's equidistributed mod 1 and you shift it, is it still equidistributed? Yeah. So we agree that the first line is equidistributed. All we have to do is understand this last little bit. Let's say we want to have a first digit of d. So here's the log base 10 of d. Here's the log base 10 of d plus 1. The danger is I could be in a very small region over here and be pushed out. Or I could be in a small region over here and pushed in. And the same thing, could be happening over here. That's the only way a digit could change. If I'm not too close to those boundaries, can this term change me by much? Right? So this is the important part. This can't move you that far. Since it can't move you that far, all we have to do is ask, well, what's the probability in the limit that we are really, really close to these extremes? And what we can do is we can play a game for every epsilon. We can show that the probability that we are sufficiently close is really, really small, and then take the limit. So when you look at the log of 1 minus something, what is that approximately equal to? So we need to get some control over the size of the errors. So how big could the log of 1 minus u be? How would you understand that? So what would we do to understand the log of 1 minus u? Taylor series. Right? The log of 1 minus u is negative u plus u squared over 2 plus u cubed over 3. If u is really small, it's approximately equal to minus u. And so what you can show is if u is small, the absolute value of the log of 1 minus u will be less than or equal to 1.1 u and will be maybe greater than or equal to 9.9, I'm sorry, 0.9 u. If u is very, very small, this will be true. You have to be careful because if u is negative, then the odd terms have different signs than the even terms. Okay, so then that means there'll be some cancellation. But if u is very, very small, u squared is so much smaller than u, it's not going to really matter. And then I should put u's in absolute values now because u could be negative. So with a little bit of algebra, you can show something like this. So you know that the log of 1 minus u is approximately the absolute value of u. So for us, the log of 1 minus 2 root 5 minus 6 over 4 to the n in absolute value will be less than or equal to 1.1 times the absolute value of 2 root 5 minus 6 over 4 to the n. And this is going to 0 exponentially fast. Right? So if we want to look at how much can this error term adjust things, so we want to count the cardinality of all n less than or equal to big N such that the log base 10 of fn mod 1 is in AB, and then divide by n. And if you want, we could take A, B to be what we want to have first digit D. I'm just doing the more general interval. So if we didn't have the error term, we know that in the limit, this is going to converge to B minus A. Can you give me an upper bound for how much trouble this error term can cause? And this is the only painful part of the proof, is we just have to show that in the limit, it doesn't change things that much. So here's A, here's B. Let's fix a small epsilon greater than 0. The only danger is if we had landed in here and were pushed below, or if we landed in here and were pushed above, then we should not be counted, but we were counted. Or we landed here and were pushed up, or we landed here and were pushed down, and we are not counting things that should be counted. So what's the probability that our original sequence, our good sequence, what's the probability in limit that n log phi lies in these epsilon balls? So what should that be in the limit since it's equidistributed? So this is our good sequence. This is a sequence that's equidistributed. Do we all agree that if our good sequence, and I don't care about the log of 1 over root 5, right? We all agree that just, so what should it be?
I don't know if it should be a finite number, but there can't be that many in that space.
Well, there could be infinitely many. But when we look at the fraction of n, so if we look at the number of, let's call these bad n less than or equal to n divided by n, what should that go to? We hope it goes to 0.
Is the number of bad n less than, would that be an expectation to epsilon?
I'm sorry?
Would that be 2 epsilon, the number of bad
Almost 2 epsilon. You're close. Not 2 epsilon.
Sorry, 2 epsilon over n.
Well, I'm dividing by n, so the 2 epsilon is almost right. 4 epsilon. Because there are 4 regions that are dangerous. My good term could land in here, 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 or here. Those are the only places where that small little error term could change us. So in the limit, the fraction of n that should go to 4 epsilon. And only if we land in one of those can this other term push us over. Okay, how likely is it for it to push us over? Well, just because we land in here, does that mean we're definitely going to be pushed over? No, this is going to be an upper bound for the change in value. Now, these terms are tending to 0 rapidly. So as n gets larger and larger and larger and larger, this is getting closer and closer and closer to 0. Because it's getting closer and closer and closer to 0, if I land over here, it's not going to be enough to push over. I've got to land damn close. But I'm overestimating right now. It's absolutely fine to overestimate. Because what we're doing is we're fixing an epsilon. And we've just shown that in the limit, the fraction of bad epsilon is at most 4 epsilon, so that our count, the count we care about, minus b minus a will be less equal to 4 epsilon for all epsilon greater than 0. Or maybe not count, maybe we should say the limiting fraction. Right? We know that n log phi is equidistributed, so in the limit it lands between a and b with a fraction of b minus a. What could the fraction be that's bad? Well, it's going to be at most 4 epsilon. Not all of those will be bad, because if we've landed over here, once n is huge, it's not going to be enough to shift it over. Similarly, if we're over here, it's not going to be enough to shift it past. The other thing, of course, is you could land in here. This term is half the time it's negative, half the time it's positive. You could land in here, and it could be pushing you closer to A, so that you're not going to get past B. And conversely, over here, you could be being pushed further away from B. So just because it has the potential to push you in the wrong direction doesn't mean it's always going to do that. We just need a bound. We can show that this is true for every epsilon, and therefore we win at the end of the day. So this proves that the Fibonacci numbers are better. Yes?
I'm confused by what you mean by limiting fraction we care about.
So that's this fraction. We know because because n log phi is equidistributed, if we just used n log phi, we would have gone in b minus a for this. If we used log of 1 over root 5 plus n log phi mod 1, that would also work, because the log of 1 over root 5 just translates everything. So the only reason we're not done yet is we have that really small tweaking error. Then it becomes, I don't know if anybody's actually studied this, so I'll pose this as a problem. Are there infinitely many phi whose first digit is changed by the small error? We've shown that in the limit, the fraction that matters is insignificant. I will make this worth a large number of excused homework problems. Can you prove or disprove that there are infinitely many phi that are this close? And if it hasn't been done, then this could be a short note that we could get published in a journal. So my feeling is it's probably going to be very, very hard to have the first digit change. Right? To have the first digit change, you've essentially got to be 1 zzz or 9, one of those two things. As soon as you have one digit that's not a 9 or a 1, or a 9 or a 0, it's not going to be enough. So it's how often are you close to a perfect power of 10 or one less than a perfect power of 10? So I will leave that as a problem to look at. Right. So this was the Fibonacci's. So the question is, what happens if you look at other recurrence relations? So let's consider an plus 1 is 2an minus an minus 1. Okay. What else do I need to give you? Starting values. So let's consider an, let's do a0 equals 0, a1 equals 1. All right, can somebody tell me what a2 would be? 2. What would a3 be? 3. We have enough of a pattern now. What's an? N. So I'll leave that as an exercise. Is this sequence Benford? Not Benford. Because if you look at it, if I stop at like 199, I've just gone through 100 numbers out of essentially 200 that have a first digit of 1. If I stop at 999, I've just gone through 800 numbers that don't have a first digit of 1. So for this problem, the percent of first digits of 1 is going to oscillate between essentially 1/9 and 5/9. So the limiting probability here doesn't exist. All right, this was a bad choice. Let's not choose 0 and 1. Let's choose a0 equals 1 and a1 equals 1. What does a2 equal? 1. A3. All right, and the pattern should be clear. Also not Benford. Although at least here the digit bias exists. And it's a very strong digit bias. So the question is, what is going on? Why do we have such a bias in this case? Why don't we get Benford behavior? Well, let's go back to how we found Binet's formula. So Binet's formula is one of my favorite equations in all of mathematics. Let's consider the characteristic polynomial. The way you solve these is you guess, an equals r to the n. You plug that in, you find what roots work, and then because it's linear combinations of roots work. So for us, we have an plus 1 minus 2an plus an minus 1 equals 0. R to the n plus 1 minus 2r to the n plus r to the n minus 1 equals 0. It was wonderful lecturing on this in the Boston area. I didn't have to worry about the accent. We can divide out by r to the n minus 1, and we get r squared minus 2r plus 1 equals 0. We're running out of time. Can somebody quickly factor this for me? Yeah, they're both minus 1. So this has repeated roots, and the absolute value of the repeated roots are 1. So it turns out the general solution is an equals c1 n r to the n plus c2 n r, c2 r to the n, where r is the root. I'm just writing it like this because since the root is 1, you're not going to see the 1 to the n. And you'll get the solution is just an is c1n plus c2. And I'll maybe spend a minute or two at the start of the next class as to why this is the solution when you have repeated roots. But what's going on is for Benford behavior, the absolute value of the largest root can't be 1. If the absolute value of the largest root is 1, you don't have Benford. If you have a unique root of largest absolute value and it's not 1, then you will have Benford's law. And we'll prove that next time. All right, this is a good place to stop.